Now that we have the subtour elimination constraints in hand, we should start thinking about solving the separation problem for them. We can recall what the separation problem is. We're given a set of feasible solutions, x. In this case, x is the set of all feasible solutions to our original integer program. In this case, the integer program is going to include all the subtour elimination constraints. Our polyhedron P is going to be defined by the linear programming relaxation of this integer program. Our solution, x star, is now going to be x star y star. And we're going to say that this solution falls inside of our polyhedron. We're also going to assume that x star y star don't define a feasible solution in terms of x. We're also given our set of constraints, in this case our subtour elimination constraints. And so that we can recall, our subtour elimination constraints are the sum of the y's being less than or equal to the sum of the xv's if we look at all the x's inside of a particular set and all the edges completely contained inside of that set. Our objective is to find a particular constraint, C, inside of our capital C, that's violated by x star. The alternative output is that there is no such constraint that's violated, and our separation procedure is going to give us a guarantee of that. We're going to solve this separation problem by introducing a quadratic program, showing that this quadratic program is equivalent to an integer program, and then showing that it has a totally unimodular constraint matrix, and so can be solved polynomial time with a linear program. To start, we just take note of the fact that our constraints are written so that the sum of the y's is less than or equal to the sum of the xv's, where we've eliminated a particular node k out of a set S that's a subset of our nodes that excludes our start node, S. In order to have a violated constraint, we'd like the sum of the y's to be greater than or equal to the sum of the xv's, with this k excluded, for this set S. Note here that ye star and xv star are both constants. This is the solution that's given to us as input. The variable that we'd like to optimize over here is actually the subset S. And so we're going to write a program that's going to find an S that will find either a violated constraint or verify that all these constraints are satisfied. To do this, we're first going to make a little bit of a notational change. We're going to introduce E' and N'. E' is the set of all edges that aren't adjacent to the node S. That is, we take all the edges in E and subtract delta S, all the edges adjacent to our start node S. This is because in our optimization, or rather to find our constraint, S isn't included. For the same reason, we introduce N', which is equal to the set of nodes V with S subtracted. Our quadratic program is going to fix the node K that is removed from our set S. To solve this separation problem more generally, we would iterate over all K's. Because there's at most n different possible values for K, we can solve this particular separation problem, where K is fixed, n times, in order to solve the separation problem in the most general way. Our quadratic program is going to rely on a set of variables zi. Zi is going to be 1 when we include node I in our set S associated with the violated constraint, and it's going to be 0 otherwise. The set of variables zi are going to tell us which nodes are included in S, but also which edges are completely contained inside of S. We note that if zi and zj are both equal to 1, then the edge ij is also completely contained inside of S, and we note that by taking the multiplication of zi with zj. Zi times zj is going to be 1 exactly when an edge, ij, is included completely inside of our set S. Note that in this program, z of k is always equal to 1. This is because K is this special node that we've decided to exclude from all sets under consideration. By doing that, we are excluding K from the sum of the xi's in our constraint. However, we're not excluding K when we're talking about the edges that are completely contained inside of S. And so we set z of k equal to 1 in order to have the right interpretation in terms of edges. Now we can interpret our objective function. Our objective function is trying to find the maximum difference between the sum of the yi's and the sum of the xi's over all sets S. If we find the maximum difference, then we find the maximum amount that a constraint can be violated, choosing over all potential sets S. Here, choosing over all potential sets S is encoded as choosing a vector of zj's. Specifically, if we find that r of k is greater than or equal to 0, or rather greater than 0, then we can verify that we have found a constraint that's going to be violated. The constraint is encoded in all of the z's, where z of I is equal to 1 if I is in S. However, if r of k is less than or equal to 0, then because this is the maximum difference between y's and x's over all sets S, then we know that there is no violated constraint, at least not for this particular choice of k. And so all constraints for this choice of k are going to be satisfied. In this way, solving the quadratic program is going to give us either a violated constraint or tell us that all the constraints are going to be satisfied. Now that we have this quadratic program, we'd like to turn it into an integer program, and specifically a linear integer program. To do that, we take the quadratic portion, which is only zi times zj, and replace it with a new variable we. We is going to be interpreted as the multiplication of zi times zj. It's easy to verify that we has to be less than or equal to zi and less than or equal to zj. It's also easy to verify that we has to be greater than or equal to zi plus zj minus 1. We include the constraint that we has to be either 0 or 1, and that zi has to be 0 or 1, and also our constraint that zk is equal to 1. In this integer program that we've written, the top set of constraints, boxed in pink, form a totally modular constraint matrix. This is easy to verify because effectively these we's are two identity matrices pushed against one another. However, the other constraint, that we is greater than or equal to zi plus zj minus 1, breaks the totally unimodular property. However, we can sort of recover the totally unimodular property by noting that we're working with a maximization problem. Because this is a maximization problem, and because all ye stars are positive, we'd like to make we as large as possible. This means that we doesn't really need to be constrained by a minimization, and effectively we is going to be equal to the minimum of zi and zj. To encode that, we only need the constraints in this pink box, the totally unimodular constraints. The other constraints, that we is greater than or equal to zi plus zj minus 1, are completely redundant. And so by eliminating this constraint, we haven't lost anything in our problem. Now we have an integer program with a totally unimodular constraint matrix, which happens to be a linear program. And so we can solve the separation problem for a fixed value of k in polynomial time. This allows us to solve this separation problem more generally.